I welcome you all to this digital classroom for the subject control systems. In the previous lecture, we solved few of the example problems related to route stability criterion and we tested for stability. Today, we are going to look into the special cases with respect to route stability criterion. If one of the following cases occurs, a suitable modification of the array calculation procedure must be made. We have two cases here. The first case is there is a 0 in the first column, but some other elements of the row containing the 0 in the first column are non-zeros. This is a special case in which there is a 0 in the first column and the rest of the element in the same row will not be 0, that is non-zero. And how do we proceed if you encounter such kind of situation? In case 2, there is a 0 in the first column and other elements of the row containing the 0 are also 0, which means that a row with complete 0. We can call it as a 0 row. This leads to case 2. This is a different situation. The first situation is different, in which only the first element of a row is 0 and the rest of the elements are non-zero. It can have any values like 1, 2 or any of the integers. Whereas in the second case, the complete row becomes 0. With respect to these two cases, the route stability criterion fails and hence we have to do some modification with respect to the route stability criteria to test for stability. That is what we are going to look forward. So let us try this problem. Given a polynomial s power 5 plus 2s power 4 plus 3s cube plus 6s square plus 2 plus 1 equal to 0. First, let me write the s terms. S power 5, s power 4, s cube, s square. And let me fill up the first two rows. Coefficient of s to the power 5 is 1 and s to the power 4 is 2. Then s cube is 3 and coefficient of s square is 6, followed by coefficient of s is 2 and the constant 1. Once after filling up the first two rows, to find the first element of the third row, we have to make use of the formula 3 into 2 minus 1 into 6 divided by 2. I get 0 here. Make a note of it. I told you, case 1, if the first column of a row is 0 and the rest of the elements in the first column 0 will be non-zero. To find the third row second element, we can trace using 2 into 2 minus 1 into 1 divided by 2. 2 2s are 4 minus 1 divided by 2. Hence I get 1.5. The third row second element is 1.5. To fill up the fourth row, the first element can be obtained by 0 into 6 minus 2 into 1.5 divided by 0. We get infinity. This leads to a special case 1, which I told you right now, and the routes array failed. As we couldn't able to interpret with respect to the first column of the route array which we are going to generate, this route stability fails. Hence, we have to do some modification with respect to this route array and we have to test for stability. Here, the routes array fails. Now, what is the solution to proceed further? We can replace 0 by epsilon, which is a very small positive value. Once after replacing 0 by epsilon, then we can interpret with the route array which is generated. Hence, let us replace 0 by epsilon, where epsilon is a very small positive value. In this case, 0 has been replaced by epsilon. Now we can fill up the fourth row, making use of the previous two rows as reference, and we can get the fourth row first element as 6 into epsilon minus 2 into 1.5 divided by epsilon. Now let us look into the sign of the fourth row first element, which is given by 6 epsilon minus 3 divided by epsilon. As I told you that epsilon is a very small positive value, 6 epsilon becomes very negligible, and epsilon in the denominator also becomes very negligible. Hence I have a negative sign with respect to the fourth row first element. Then the fourth row second element can be given by epsilon into 1 minus 2 into 0 divided by epsilon, which is 1. Epsilon will get cancelled out. We get 1. And the fourth row third element will be equal to 0. To fill up the fifth row, we have to make use of the previous two rows as a reference, and the pattern is given by 6 epsilon minus 3 divided by epsilon into 1.5 minus epsilon into 1, the whole divided by 6 epsilon minus 3 divided by epsilon. Now let us look into the sign with respect to fifth row first element. I have represented here separately, in which 6 epsilon is very negligible, as epsilon is a very small positive value. We get 1.5 into minus 3 minus epsilon square is again a very small positive value, hence it is very negligible. I get minus in the numerator, and here in the denominator 6 epsilon is negligible again, hence I get minus 3. So I have a minus in the numerator and minus in the denominator, hence it will be plus here. The sign is positive with respect to fifth row first element, and fifth row second element, hence the sign is positive. Hence I can write that the sign is positive. Now the fifth row second element will be equal to 0, and to fill up the last row we have to follow the pattern. The previous element multiplied by 1 minus 6 epsilon minus 3 divided by epsilon into 0 divided by again the same element. We get 1 for the last row first element. And the rest of the two elements will be equal to 0. Once after generating the route array, we have to interpret with the route array, looking into the signs of the first column of the route array. Hence, by this method, 0 has been replaced by very small positive value epsilon, and we could able to compute for all the elements, and we could able to identify the sign with respect to the first column of the route array. Now the next step is to interpret with the route array representing the sign of the first column of the route array. So the first column, the first element is positive, the second element is positive, the third element as epsilon is a very small positive value, it is positive, and the fourth element is negative, the fifth element is positive, and the sixth element is positive. Now we have to look into whether there is any sign changes with respect to the first column. Positive to positive, no sign change. Positive to positive, no sign change. Now from positive to negative, do we have a sign change? Yes, I have one sign change. Then from minus to plus, again I have another sign change, so I can number it as 2. If you continue further, it is from plus to plus, no sign changes. Hence, we have a total of 2 sign changes. As there is a sign change, you can say that the system is unstable. In addition to that, it conveys me that there are 2 rows which is present on the right half of the S-plane, which is making the system to be as unstable. Hence, you can conclude that there are 2 sign changes, hence the system is unstable. Let us try out with this example problem in which d of s is given by s power 5 plus 2 s power 4 plus 2 s cube plus 4 s square plus 11s plus 10. In this case, 0 is to be replaced with a very small positive number epsilon, and the rest of the array can be evaluated. So it is a special case of route stability criterion, and we can call it as case 1. First, let me arrange the s terms: s power 5, s power 4, s cube, s square, s power 1 and s power 0. Let me fill up the first 2 rows from the given polynomial. Coefficient of s power 5 is 1 and coefficient of s power 4 is 2. Hence I can write 1, 2 followed by 2, 4 continued with 11, 10. To fill up the third row, the first element can be written making use of the formula 2 into 2 minus 1 into 4 divided by 2. I get 0. Now 0 can be replaced by epsilon. Third row second element where epsilon tends to 0, which means I can take epsilon to be as a very small positive value. And to fill up the third row second element, I can trace using the pattern 2 into 11 minus 1 into 10 divided by 2. Hence I get 6. And the third row, third element will be equal to 0. To fill up the fourth row, I can take the previous 2 rows as a reference. And I can find the fourth row first element as 4 into epsilon minus 2 into 6 divided by epsilon. I can represent it as C1, and if I substitute for epsilon as a very small positive value, 4 epsilon becomes negligible and epsilon in the denominator becomes negligible. Hence I get a negative sign. Then the fourth row second element can be filled making use of the pattern epsilon into 10 minus 2 into 0 divided by epsilon. Hence I get 10. And the fourth row third element will be equal to 0. To fill up the fifth row, I can make use of the previous 2 rows as a reference, and I can fill the fifth row first element d1. d1 can be given by 6c1 minus epsilon into 10 divided by c1. I have written here on the other side. And now we know that c1 is negative. Hence I get here minus 6 minus 10 into epsilon is a very small positive value divided by negative sign. We get positive sign. Then we can fill up the rest of the elements. And finally the last row, first element will be 10 into d1 minus c1 into 0 divided by d1. d1 and d1 will get cancelled out. Hence I get 10. in the third row first element, and the rest of the elements will be equal to 0. Now the next step is to interpret with the route array, looking into the signs of the first column of the route table. So if you look at the first column, and let us represent the sign of the first column. The first element is positive, the second element is positive, the third element is positive as 0 replaced by epsilon, which is a very small positive value. The third element is also positive. The fourth element we have identified it as negative, and the fifth element it has been identified as positive, and the sixth element is again positive. Now let us look into the sign changes. Plus to plus, no sign change. Again plus to plus, no sign change. Plus to minus, is there any sign change? Yes, I have a sign change. How many? It's 1 as of now. Again it is moving from minus to plus. Hence again I could able to see another sign change. I can number it as 2. I could able to identify 2 sign changes so far. Now again from plus to plus, hence there is no sign changes. So we could able to find 2 sign changes in this example. Hence the system is unstable and there are 2 sign changes which clearly says that there are 2 poles in the right half of the S-plane. Hence making use of case 1, which states that if you encounter any of the first element, that is in a particular row, if the first element is 0, that is the first column is 0, and the rest of the elements in that particular row is non-zero, then we have to replace 0 by epsilon, which is a very small positive number, and we have to further proceed and we have to interpret with the route table to find out the sign changes. And finally, we have succeeded in identifying the sign changes and we could able to test for stability for this case. Let us move on to the next problem. Comment on stability using route criteria if characteristic equation is given by q of s is equal to s to the power 5 plus 2s power 4 plus 3s cube plus 4s square plus 5s plus 6 is equal to 0. How many poles lie in right half of S plane? We know the procedure. First, let us write the routes table. With respect to a square row, the first element, if you trace 1 into 4 minus 2 into 4 divided by 1, it becomes 0. Hence, we have replaced 0 with a very small positive value, that is epsilon. Then we have continued solving this problem which we have discussed right now. And if you look into the fifth row, first element, it is 2 epsilon minus 6 divided by epsilon. After following the pattern, let us identify the sign here as epsilon is very small positive value. It is very negligible. I get minus 6 divided by again epsilon. It is a very small positive value. Hence it is negligible again. Hence I get a negative sign here. Now we can interpret with the first column of the route array and represent the signs of the first elements. Positive, positive, positive. Epsilon, as it is a very small positive value, I can write it as positive. And for the next element, it's negative, which has been identified here, and again positive. So if you inspect throughout, there is 2 sign changes from positive to negative 1 and negative to positive 2. Hence, there are 2 sign changes in the first column. Hence, 2 poles lie in the right half of the S-plane and the system is unstable. This is again the same case which we discussed right now. Let us try to solve this problem in which a given polynomial d of s is power 6 plus 5 s power 5 minus 2s power 4 minus 3s cube minus 7s square minus 4s minus 4 equal to 0. So the first step is to represent in a form of a row array. Let us fill up the first two rows, taking the coefficients of s power 6 and s power 5, continued with s power 4 and s power 3 coefficients as minus 2, minus 3, followed by minus 7, minus 4, and minus 4, 0. Now to fill up the third row, we have to make use of the previous two rows as a reference, and we have to follow the pattern 1 into minus 2 minus 1 into minus 3 divided by 1. The third row first element I get 1, and the second element, if you continue with the same formula, I get minus 3, and the third row third element will be minus 4. Similarly, to fill up the fourth row, I have to make use of the previous two reference, and the fourth row first element can be written as 1 into minus 3 minus 1 into minus 3 divided by 1. I get 0. To fill up the fourth row second element, I have to trace with the pattern 1 into minus 4 minus 1 into minus 4 divided by 1. Again I get 0. And the fourth row third element will be again 0. So in this case, I could able to see a complete row as 0. Recall the second case which I introduced in the beginning of the session, that there is a 0 in the first column and the other elements of the row containing the 0 are also 0. That is, we have a 0 here in the first column, yes, and the other elements of the row containing the 0 is also 0, which means it is a case 2 in which we could able to see complete 0 row. Hence in this case the entire row becomes 0. If the entire row is 0, then we cannot proceed further, and now again the route stability criteria fails. Hence, we have to form an auxiliary polynomial with a row immediately above the complete 0 row. So, with respect to the row above the complete 0 row, I could able to see s power 4 row, and I have to form an auxiliary polynomial. Hence, to solve the problem, from s power 4 row, we obtain an auxiliary polynomial, which is given by a of s is equal to, as it is s power 4 row, we start with s power 4. The coefficient of s power 4 is 1. Then the next term will be minus 3s square and minus 4. The auxiliary polynomial will always have the highest power as even, and the rest of all the terms will be also even. You could able to see here s power 4, s square, and s to the power 0. Let us recall the characteristic equation from which we represented the first two rows. That is s power 6 plus 1 into s power 5, which has been represented here, then followed by minus 2 s power 4, continued with minus 3 s cube, then with minus 7 s square, continued with minus 4s minus 4. Hence you could able to see here the first row it's of the form the coefficient of s square followed by coefficient of s power 4, that is minus 2, followed by coefficient of s square, that is minus 7, followed with the coefficient of s to the power 0, that is minus 4. Similarly, if you have to represent for s to the power 4 row, it starts with 1 into s power 4 minus s cube term comes down here. Hence, this is minus 3 into s square, and s to the power 1 term will be beside it. Hence, this will be minus 4 into s to the power 0 term, which has been written here. Once after representing the auxiliary polynomial, We have to differentiate this auxiliary polynomial with respect to s. So let us differentiate. Hence, d by ds of a of s is given by, we know that a of s is s power 4 minus 3s square minus 4. Hence, hence if you differentiate it with respect to s, we get 4s cube minus 6s minus 0. Hence, I get 4s cube minus 6s. Once after differentiating, we have to replace the complete zero row with the coefficients of the derivative of the auxiliary polynomial which we have obtained right now. Also, if you encounter a situation like this with complete row as 0, which indicates that there are two roots on the j omega axis, and we know that if the roots are present in the imaginary axis, the system becomes marginally stable. Hence, the complete 0 row indicates that the system is going to be marginally stable. You can make a note of it. Now let us replace the complete 0 row with the coefficients of the derivative of the auxiliary polynomial coefficients. Let the terms in s cube row be replaced by 4s cube minus 6s. Then the array can be represented as the complete 0 row, that is s cube row, now can be replaced by the coefficient of s cube is 4. Hence, I can replace the complete 0 row as 4 and minus 6, which are the coefficients of the derivative of the auxiliary polynomial, where s cube coefficient is 4 and the s coefficient is minus 6. Once after replacing the complete 0 row with 4 and minus 6, now we can continue further making use of the procedure which we used to follow for filling the route array. Hence, a square row can be determined making use of the previous two rows as a reference. Hence, a square row, the first element is given by 4 into minus 3 minus 1 into minus 6 divided by 4. I get minus 1.5. Similarly, we can fill up for the rest of the rows. As we have done so many problems, we know how to proceed. Once after representing the route array, the next step is to interpret looking into the first column of the route array, and we have to inspect the sign changes. The first element is positive, second positive, third positive, fourth positive, fifth negative, sixth negative, seventh negative. So if you keep on checking for the sign changes, no sign change, no sign change, no sign change, positive to negative, yes, I have one sign change. Now negative to negative, no sign change, no sign change. It is very clear that we could able to see one sign change in this example. There is one sign change of the first column of the array. Hence, only one pole lies in the right half of the display. This is a different case in which we have encountered a complete row as 0 and we have taken a row before the complete 0 row as an auxiliary polynomial, and we differentiated the auxiliary polynomial with respect to s, and we took the coefficients of the derivative of the auxiliary polynomial and we replaced the complete 0 row with those coefficients of the derivative of the auxiliary polynomial. And then we continued simplifying the route table and we interpreted, and now we could able to find whether the system is stable or not. These are the two possible cases which we could able to face while we are interpreting with the route table. Let me try out with this example. The given polynomial s power 6 plus 4s power 5 plus 3s power 4 minus 16s square minus 64s minus 48 equal to 0. Find the number of roots of this equation with the positive real part, negative real part, and find the number of rows of this equation with positive real part, zero real part, and negative real part. Let us solve this problem. The first step is to generate the route table. And if you try to generate this route table, this is a special case in which you could able to see that the complete row becomes zero. So this is a special case subjected to case 2. So we know the procedure now. We have to take the row before the complete zero row as an auxiliary polynomial. Hence, let me represent the auxiliary polynomial a of s as 3s power 4 plus 0s square minus 48s power 0. Hence, a of s is given here. Now, the next step is to differentiate a of s with respect to s. Hence, d by ds of a of s is given by, if you differentiate, I get differentiation of 3s power 4 is 12s cube, and this is a constant, hence I get 0. Now the next step, we know that we have to replace the complete zero row with the coefficients of the derivative of the auxiliary polynomial. We have the coefficient of s cube as 12. So let us replace the complete zero row with these coefficients. Once after replacing, s cube row is represented as coefficient of s cube is 12 here, hence 12, 0, 0, 0. Now to fill up s square row, I have to make use of the previous two rows as reference and I have to proceed further. The first element is given by 12 into 0 minus 3 into 0 divided by 12. Hence I get 0. If we proceed further, for s square row, the second element is 48. I get this pattern making use of the formula 12 into minus 48 minus 3 into 0 divided by 12. 12 in the numerator and in the denominator get cancelled out, hence I get minus 48. Now if you notice this, it is very clear that in a particular row, the first element, that is the first column, is 0 and the rest of the element is non-zero. Hence it is a special case 1 in which 0 has to be replaced by epsilon, a very small positive value. Hence I have replaced 0 by epsilon, a very small positive value. And then let us try to proceed further. So the s to the power 1 row, the first element is given by epsilon into 0 minus 12 into minus 48 divided by epsilon. Hence I get 576 divided by epsilon. Let us fill up the rest of the elements. And finally, s to the power 0 row can be given by 576 divided by epsilon into minus 48 minus epsilon into 0 divided by 576 divided by epsilon. 576 divided by epsilon in the numerator and the denominator will get cancelled out. Hence I get minus 48 for the first element of s to the power 0 row. Once after obtaining the route array, we know the procedure. We have to interpret with the first column of the route array and identifying whether there is any sign changes. The first element is positive, second element is positive, third element is positive, fourth element is positive. 0 replaced by epsilon, which is a very small positive value, hence again it is positive. 576 divided by epsilon, epsilon is very negligible, I get positive. The last term is minus. Hence throughout there is no sign change. From the last element, from the last before element towards the last element, I could able to see one sign change. Hence I can say that as there is one sign change, the system is unstable. But in the question, they have asked you to find the number of roots of the equation with the positive real part, zero real part, as well as a negative real part. So now let us try to find out number of roots of this equation with positive real part, zero real part, and negative real part. Therefore, there is one sign change and the system is unstable. Thus, there is one root in the right half side of the S-plane, that is, with positive real part. So it is very clear that as we have one sign change, which is making the system to be as unstable, we have one root in the positive real part. Now, let us solve the auxiliary polynomial a of s is equal to 0 for finding the dominant roots. We know the auxiliary polynomial which has been obtained in the previous slide as 3s power 4 minus 48 equals to 0. Let me replace s square equal to y. Hence I get, substituting for s square is equal to y in this auxiliary polynomial, I get 3y square minus 48 equal to 0. Hence 3y square is equal to 48. Hence y square will be equal to 48 divided by 3. Y square will be equal to 16. Therefore, y square will be equal to 16. Hence, y will be square root of 16, which is given by plus or minus 4. But y is s square. Hence, let me replace y by s square. Hence, s square equal to plus 4, we get s is equal to plus or minus 2. And for s square is equal to minus 4, we get s is equal to square root of minus 4. Hence, I get plus or minus 2j. That is square root of minus 4 that is square root of minus 4. Square root of minus 1 is square root of minus 4. I can write it as square root of minus 1 into square root of 4. Square root of minus 1 is j and square root of 4 I get it as plus or minus 2. Which has been represented here. Hence, from this expression, it is very clear that as we get s is equal to plus or minus 2j, there are two roots on the imaginary axis, whereas s is equal to plus 2 clearly shows that this root is lying in the right half of the S-plane. In the given question, the polynomial is s power 6, so we have total 6 roots. And out of these 6 roots, one root is lying in the right half of the S-plane and two roots are lying on the imaginary axis. Hence, the roots with negative real part can be given by the total available roots minus two roots on the imaginary axis minus one root which is on the right half of the S-plane. Hence, 6 minus 2 minus 1 which will be equal to 3. From this it is very clear that I have 3 roots in the negative real part. So with respect to the given question, to find how many roots are present in the negative real part is 3 and how many roots are present in the positive real part is 2 and how many roots are present in the 0 that is the imaginary axis is plus or minus 2j that is 2 roots are present in the imaginary axis. So we have done with this problem and let us try out with this example problem. Using RH criterion, determine the stability of the system having the characteristic equation given by s power 6 plus 2s power 5 plus 5s power 4 plus 8s cube plus 8s square plus 8s plus 4 is equal to 0. So first let us formulate the RH table and write the first two rows which you are very familiar with. Now to fill up the third row, make use of the pattern 2 into 5 minus 1 into 8 divided by 2. I get 1. Similarly, the second element will be 4, third element again 4, and the fourth element is 0. Let us try to continue further, filling the fourth row, that is S cube row. When you try to proceed, we get the complete row as 0. Now we know the procedure. We have to take the row previous to the complete 0 row as an auxiliary polynomial. Hence, A of s is given by 1 into s power 4 plus 4 into s square plus 4. Hence, this is a special case. I have written the auxiliary polynomial which I told you right now. And now I have to differentiate this auxiliary polynomial. S power 4 differentiation is 4s cube. And 4s square differentiation is 8s. And differentiation of 4 is 0. Now once after differentiating the auxiliary polynomial with respect to s, I have to take the coefficient of this derivative auxiliary polynomial and substitute in the complete 0 row. Here I have the coefficient of s cube as 4 and the coefficient of s as 8. Let us fill up in the complete 0 row as 4 and 8. And we have to continue the procedure of filling up of the rest of the rows, making use of the previous 2 rows as a reference and following the procedure. So to fill up the s square row, we have to make use of the previous 2 rows as a reference. Hence, I can make use of the pattern 4 into 4 minus 1 into 8 divided by 4. Hence, I get 2 for the first element. The second element is given by 4 into 4 minus 1 into 0 divided by 4. I get 4 in this case. Similarly, if you try to fill up the s to the power 1 row, I have to make use of the previous 2 rows as a reference and fill the first element of the s to the power 1 row. Hence, I can make use of the pattern 2 into 8 minus 4 into 4 divided by 2. 8 2s are 16 minus 4 4s are 16. So the first element is becoming 0. If we continue further, the complete row becomes 0. And again, it leads to the special case 2. Hence, we know the procedure. Now we have to take the previous row of the complete 0 row as an auxiliary polynomial, which is given by 2s square plus 4. If I differentiate this auxiliary polynomial, 2s square differentiation is 4s, and I can take the coefficient of s and I can replace the complete 0 row with the derivative of the second auxiliary polynomial. So I can write it as 4, 0. Now to fill up the last row, I have to take the previous 2 rows as a reference and I have to proceed further making use of the formula 4 into 4 minus 2 into 0 divided by 4. 4 4s are 16 minus 2 into 0 divided by 4. 16 by 4 we get 4. One of the most important thing to be noted down here is in the beginning while filling up the 2 rows we have written the coefficient of s to the power 0 as 4 and you could able to see the shift in this coefficient of s to the power 4 throughout this route table diagonally. And finally, with respect to the last row s to the power 0, we get the same coefficient which you could able to notice here in the question. You can go back and inspect for all the characteristic equation and analyze with the route array. The final s to the power 0 will have the coefficient which is specified in the question itself. Now we have generated the route array, or we can call it as a route table also. And if you look into the first column, we could able to see there are no sign changes, hence you can say that the system is stable. But on the other side, I told you very clearly that if you encounter a complete zero row, which means that there are roots on the imaginary axis. If you process with the auxiliary polynomial equated to 0, we could able to see few roots on the imaginary axis. Hence now we have to equate the auxiliary polynomial equal to 0 and find out the roots on the imaginary axis, which makes the system to be as marginally stable. Hence, as I told you before, there are no sign changes in the first column, so no roots on the right half of the S-plane. But you cannot declare that the system is stable because it is a special case too in which the complete row is becoming 0. That's the reason I told you to equate A of S is equal to 0. Now I have equated S power 4 plus 4S square plus 4 equal to 0. If we simplify further and if I find out the roots of this equation, I get S square equal to minus 2. And again S square is equal to minus 2. Which means I got able to get 4 roots which are repeated roots. I get S is equal to plus or minus J 1.414 and again plus or minus J 1.414. Hence, there are repeated roots on J omega axis. We know that in the beginning of the introduction class, I told you that if there are repeated roots on the imaginary axis, it makes the system to be as unstable. Hence, now in this case, the system is unstable in nature. The location of the roots on the imaginary axis has been represented here. You can have a look at it. Let us recall this and you can make a note of it. The non-repeated pair of roots located on the imaginary axis are as shown here. If it is non-repeated roots, I can say that the system is marginally stable. Whereas the repeated pair of roots located on the imaginary axis is shown here, and in this case, the system becomes unstable. In this session, we have done with the two special cases with respect to route stability criterion, and we could able to interpret with the first column of the route array, and we can test for stability, making some modification with respect to the route stability criterion. In the next lecture, let us discuss about the relative stability analysis. Thank you.